Okay, so this, what I'm about to show you, should look familiar to you.
Yeah.
If it doesn't, then I'm going home. What is that?
Aren't you home already?
No.
Oh, okay.
What is this?
Motorcycle.
Somebody besides Nick. Okay, well, I guess I'm going home. See ya.
Motor starter.
I was muted. I was muted.
Thank you. Thank you. It's a motor
Sorry.
starter. Good grief. This is missing the overloads, but all it is an iceberg relay. It's not an iceberg. It's a control
Yes.
relay, right? So here's a control relay. All we're doing is using a coil to control these 4 contacts, right?
Yeah.
This is the same thing. There's 3 sets of contacts. So this will start and stop a 3-phase motor with this coil making contact between this point and this point, right? That's all a motor starter does. It's just like this with overloads. Now, what do we have to do to reverse the direction of a 3-phase motor?
I know you don't want me to answer. Go ahead.
Swap.
You're on the right track. Swap what?
Just swap the leads.
How many?
2.
Any 2.
I don't think any 2. Maybe
Any 2.
Any 2.
Any 2. Swap any
Okay.
2 of the leads on a 3-phase motor will reverse the direction. And let
Okay.
me show you what happens when you do that. Whoops. A phase, B phase, C phase. So here's your sine wave. This is happening 60 times a second, right?
Yes.
Now you remember what I told you about how with a 3-phase motor we're creating that rotating magnetic field?
That push and pull.
Right, and let's just use Y as yeah, exactly. Let's use Y as an example. So I'll use you 3 for an example. So here you guys are with your big giant hammers. Why are you giggling?
No.
So Nick, you're going to be phase 1, so you're red. So when Nick phases, he swings his hammer. Okay.
All right.
Tyler, you're phase 2, so when the blue phase peaks, you swing your hammer.
Ding.
Huh?
I said ding.
Ding, but your hammer's not as big as Nick's. Garrett
Yep.
got the biggest hammer out of all of you guys. He swings his hammer when the black phase 3 hits, right? So if you think about this in terms of these windings are going to get energized when you guys peak. And I know there's the whole push-pull magnetic polarity thing happening, but it's easier for me to explain when, like if you're on a merry-go-round and Nick pushes, then Tyler pushes, then Garrett pushes, okay? So here we're going red, blue, black, right? So Nick, Tyler, Garrett, Nick, Tyler, Garrett. And you can see how that creates a rotation like this, right?
Mm-hmm.
So let's switch 2 of those phases. So let's put Tyler over here, and let's put Nick over here. So what color are you?
I'm red.
Nick, you're red, right?
Yep.
Tyler's blue. So we're going to go Nick, Tyler, Garrett, Nick, Tyler, Garrett. So Nick, Tyler, Garrett. And you can see how that creates a rotation this way, right?
Opposite.
So it just reverses the direction of that rotating magnetic field. And just to prove to you that any two would work, let's put Nick and Tyler back to where they were at the beginning, and let's change Tyler and Garrett. Okay, so Nick's red, Tyler, you're blue, and Garrett, you're black, right? So Nick, Tyler, Garrett, Nick, Tyler, Garrett. And you can see how that still reverses the direction, right? So switching any two of those phases is going to reverse rotation. Where the beginning, when we first started this, we were clockwise and now we're counterclockwise. If you ever hear clockwise and counterclockwise, that's talking about phase sequence. So red, blue, black, blue, black, blue, red, black, red, blue, right? That's phase sequence, that's rotation for a motor. You understand?
Yeah.
Okay. Now that we've got that, I'm going to show you this. Look familiar?
Yep.
So this should look familiar. It's what I just showed you. And then we got this extra little schmear here. What happens with these, if you take a close look at the top, it's the same exact setup. It's a contactor, right? But you hook up incoming three-phase power to either side of this. So you could hook it up here or you could hook it up here. What happens with this is you see these little tabs up at the top. They connect those two. But if you look closely inside there, if on this side you have 1, 2, 3, 1, 2, 3, these tabs right here connect this 3 to this 1. Let me see, is that doing that?
Yeah.
Reversing? No, it's these ones back here. This one connects 3 to 1. This one connects 2 to 2. And this one connects 1 to 3. So what is that doing? 2 stays the same, but the 1s and the 3s switch each other, right? So it's this motor starter, this is a forward reverse motor starter. It's protecting the same motor with the one set of overloads, but it's using these 3 tabs to reverse direction of the motor. So a forward reverse motor starter has 2 coils, okay? So let's say this one's forward and this one's reverse. When forward is energized and does, get my hand in there. Can't. Okay, so forward's energized, boom, it makes contact between these 2 points, right? So let's say that phase sequence is 1, 2, 3. When this coil is energized, it makes contacts between these points and these points. And you only have to hook incoming power up once because these things reverse 2 of the leads. They switch 2 of the leads. So when this one is energized, the sequence goes 3, 2, 1 to here, reversing the direction of the motor. Does that all make sense?
Yeah.
So that's the whole point of a forward reverse motor starter, is just to switch 2 of the leads, and it does it automatically. All we have to do is say, well, for forward direction, we want to energize this coil. For reverse direction, we want to energize this coil. Okay, so on that diagram that we can't use, or we'll have to figure out a way to use, Here is, you see these are both, there's two coils here. They're both labeled MS2. That's motor starter 2. It could be motor starter 400. It's just a number that we assign to that forward reverse motor starter. Okay. The only other thing that, so when this rung is energized, let's see, let me do this. When this coil is energized, crap, come on. Here, it's going to go in the forward direction. So let's say that's clockwise. When this coil is energized, it's going to go in reverse direction. So let's say that's counterclockwise. The last thing that I need to explain to you about these is on those motor starters, remember we had an auxiliary contact that tacks onto the side of it. And that's what we use for a seal in or a holding contact.
Yeah.
Those forward reverse also come with the normally closed auxiliary contact. And that is for something called an interlock. Yeah. An interlock are these two things right here. They're normally closed contacts. So those two sets of normally closed contacts, you see how the one on the forward rung is for the reverse coil, and the one on the reverse rung is for the forward, or you know what I'm saying? They flip-flop, right? So reverse, reverse, forward, forward. The reason for that is when the blue coil opens, what happens to this contact?
When it closes?
When the reverse coil is energized. So we put 120 volts on this coil. What happens to the reverse normally closed contact?
It opens so you can't run forward.
It changes state, yeah. So when that coil energizes, this changes state, makes it open. The point is that we don't want to energize that coil at the same time. And then the opposite, when the forward coil is energized, it opens this so that you cannot get the reverse coil energized at the same time. It's just kind of like a safety thing.
So let me ask you, can I ask you a question?
Yeah.
With three-phase like that, if you try to operate both of them at the same time, will it introduce opposing magnetic fields and catastrophic failure, or will it just lock up the rotor?
I'm thinking it will trip any overcurrent protective device you have, because what you're doing is shorting out two of the phases, right?
Okay.
So for that motor starter, it reverses lines 1 and 3, right?
Okay, yeah, that's right.
And 2 stays the same to reverse the direction.
Okay.
So if you energize both those coils at the same time, it would direct short 1 and 3, which would be
bad.
If your overcurrent protective device is fast acting, then it'll just trip or blow the fuse. If not, it'll burn some stuff up.
Probably get some welding going on, huh?
Yeah, I don't think it's going to have enough time to do any damage to the motor, but yeah, that's why we put interlocks in there.
Okay.
All right.
Do they have the new rules are they have to be both electrical and mechanical interlocks, right?
I'm not aware of that. That might be I'm not sure.
Okay.
Are you saying it's like code, or like
whoever governs the manufacturing process of them, like whatever the entity is that they get together and they decide all this? Because I know that most of the major manufacturers, they have some kind of get together. Like when they do the NEC, most of the major manufacturers sit on the NEC board at one point or another. They have people that come in and they give their 2 cents worth about, what's for what installations and what's in what field and stuff like that. But all the ones that I've seen lately, they have to be both mechanical and electrical. all the IEC ones are, and all the ones. So you can't physically, like a technician that doesn't know any better can't physically go in and push both of them at the same time.
Right.
You can't. Yeah.
Okay. On this print, you see LS1 and LS2. You probably figured out what LS stands for by now, right?
Yeah.
Yeah?
Yeah, I know what it means.
So those are shown as a, I guess you'd call it normally closed limit switch. And then you could have a normally closed held open.
Yep.
You could have a normally open. Wow. And you could have a normally open held closed. So these two are the ones you would normally see on a print because they're shown in their de-energized states. These two are the held ones. But all the same symbol. And when it comes time to actually using one of these, a lot of that, typically what you'll see is like a housing that this thing snaps into, but they all operate the same. And on the trainer behind me, like they have ones that this operates pretty simply, right? So if this is on a conveyor, something comes down the conveyor, it'll push on this little roller as it goes by, which will do whatever it needs to do. You're going to count, or you're going to stop something, or right.
Yep.
Huh?
Yeah, I was saying yeah.
Oh, okay. So this thing normally sits on like a housing so this housing would screw onto whatever, and then this thing would plug in. I don't have any of those with me. I've got some on the trainer behind me, but this is the important part because this shows how this thing hooks up. This one's the same deal, but it's all included in one package, and the cover just goes on top. But if you put your meter leads in here, I'm assuming, oh, there we got a diagram. 1 and 2 are normally open. 5 and 6 are normally closed. I'm not sure what 3 and 4 do, but we could figure that out. See, there's 6 screws in here, and then if I zoom way in, they're labeled so they can show you what to do. So these two screws would be normally open, and then when the lever is actuated, you hear that little click. That's this contact closing, and these ones opening. So if you wanted something to turn on when this thing is actuated, you would use these 2 pins. If you wanted something to turn off when it's actuated, you would use these 2 pins. So something would be normally energized here, like a light. When that's actuated, the light turns off, right? Same thing with this guy. This guy's got 2 sets of contacts, and it shows you, I don't know if can you read that? It says same polarity, and then it says 1, 2, 3, and 4. So those are the pins that on the back on the housing would actually be labeled, but they're just these 4 things that stab into that that
Yeah.
housing. So 1 and 2 would be normally open on this one, and 3 and 4 would be normally closed. Oh, and you remember I told you a while back what the dotted line stands for
Yes,
on a print?
I do.
What does that stand for?
Means they're mechanically interlocked.
Right, they're mechanically connected. So that means that you can never have this one closed and that one closed at the same time, right?
Yep.
And you will see that on prints quite a bit. What else? This is the one that was on your trainer, and I haven't even messed with these yet. Some of you guys might have. Get this little lever out of the way.
Why do older guys call them micro switches?
I'm assuming because like a brand name. I'm not really sure.
Okay.
But I'm not sure. I know this is upside down, but I really don't want to screw with the camera too much right now. But okay, so there's two. One of these, it says limit switch, but on the box it said micro switches. So I'm not really sure if it's just
okay,
like in just kind of what they used to call them kind of thing. But
all right.
These are, I'll show you, this one operates a little bit differently, but this is just a lever arm, right? This one, it actually pushes in when it actuates. So there's all sorts of different kinds, but the most common are these lever ones. So all I did there was screw this thing and push that lever arm out. So it's kind of nice that you can adjustable. These are all really cheap. Stuff that you have on your trainers is cheap. Sorry, but I have a budget. And then this will show you that pins 3 and 4 are normally open. Pins 1 and 2 are normally closed. So open this bad boy up and see what's on the inside. I haven't even really messed with these yet. Whoa.
That's interesting.
Interesting. So these 2 points are normally open. These 2 points are normally closed. So looks like you can actually even see those contacts making and breaking. So I'm going to hold it here and operate that lever arm. So what these two are normally closed, what you should see is that little plunger inside there when I operate it, pull up and make to these two. Yep.
Oh, yeah.
Kind of cool. I like
Yeah.
that. Normally limit switches, you can't
That
see
actually
those
is.
contacts making and breaking.
I think on the Allen Bradley, you can't take them that far apart and see them usually.
Jingle
In our
bell, jingle
our
bell,
book,
jingle
I was reading.
all the way.
Jesus. Are those brass
Oh,
contacts
what
or
fun it is to ride on a one.
open sleigh?
What?
Open sleigh. You got to finish.
What were you saying?
Oh, those contacts in there.
Open sleigh. Hey. Go ahead. Okay, I'm done. What?
I'm gonna need a minute.
Okay.
What I missed?
Nothing. I just kept interrupting him because I'm a jerk.
Oh my god. That's good. Good. Are the contacts usually brass in there or are they silver? Because in our book they said that they like to use like silver ionized contacts or something like that. And I thought they were either copper or brass.
They look like brass to me.
Okay. So the silver contacts would be pretty. They're saying they're becoming more usual, and I don't think I've ever seen silver contacts before.
Well, the thing is, like, a lot of times you'll see. It's hard to tell. A lot of times you'll see like the plunger on there itself will actually be brass, and then they have this silver colored, like the points of the contact. If that makes any sense, where they actually meet, like those two will be a different kind of alloy.
Okay, that actually makes sense.
So like
I've seen that before.
This one is the same thing, but I guess what I'm trying to say is a lot of times you'll see like this one, the lever arm, that looks like copper to me, and it looks like the points are brass, but sometimes you'll see these little points be a different alloy, like a silvery, probably to reduce, because when these things make and break, there's usually, like, it's very common for them to arc a little bit, and then over time those contacts get corroded and they go bad.
Well, because they said not to scrape or not to sand the silver ones, and I'm thinking back to how many times I've done that to a set of contacts, not knowing if they were silver or
I've done that
because I always thought they were just brass.
Yeah, I've done that out in the field. Just clean them up, and you're not supposed to, because it's probably not going to help the arcing. It'll probably make it worse. But if you're in the field and you don't have a spare set of contacts to replace them with, and you don't have like alcohol rubbing out, whatever. So
yeah.
But if you're just trying to get something to work, yeah. I don't know. I'm not an expert on what they make those things out of, but that would be my guess as to what the book was talking about anyway.
All right. Well, thanks for that.
Sure.
And for giving me a hard time.
One horse open sleigh. Hey. All right. So this is the one that's on your trainer. And I'm going to call this middle position is open for both of them. Yep. And that would be closing one set, and this would be closing the other set. So I'm going to put my meter on here just to see. Oh, yeah, it's just two. So it's actually physically, you could replace these. It's kind of nice.
Yep.
Yeah, so you could open this thing up if one of these goes bad and replace just that contact. But so these are open, and it will close between these two when I do that, and it will close between these two when I do that. So before we get to your trainer, let me just show you what this lab is supposed to simulate, and I'm not sure that we're going to be able to do that with the components that we have reversing the direction of the motor.
Need a reversing relay, huh?
We might be able to. We might be able to with our control relays.
Yeah, have them come in and then go out.